energy storage elements, and this is going to help us understand AC circuits better. Okay, and then before we go ahead and talk about AC circuits, I'm going to briefly, introduce us to what DC circuits are, and then I'm going to expose us to what AC circuits are, and then we can then go ahead and then start working on our AC circuits. Okay, so the first question I want to ask you is this: what is direct current? Direct current is usually abbreviated as DC. So, and it is a current with a constant time characteristics, as you can see here. A current with a constant time characteristic. So what you will look at on this graph is that you can see that we have current against the graph of current against time. And what you will see in that current against time graph is that all the time you can see that we have constant time here. The time is just constant, going from 0 to 1, it is constant, all right, and then from 1 again to 7 or till whatever it is it's getting to, you can say it's just constant again. So the direct current is characterized with a constant time graph, all right. So you can see we have a switch here. Okay, a switch is usually incorporated when we're talking about energy storage elements, because we have to find a way to either, start and stop, either charging or not charging. So you can see we have this circuit here, and then these 5 ohms and these 5 ohms, R1 and R2, are they in series or in parallel? They are in series. So if you add them together, it simply means our total R will be equal to 10 ohms. So if total R is equal to 10 ohms, what it simply means that you can find the current passing through them once you turn the switch on. Once you turn the switch on, it allows current to flow through this resistance, the resistor of 10 ohms that we have here. If you turn the switch on, and if you turn the switch off, current stop flowing. Okay, so turning the switch on makes the current to start to flow. Turning it off for this particular configuration stops the current from flowing to load, to the resistance that we have. So once you turn it on, current begins to flow. When current flows, that current will be given as V over R, which is our Ohm's law. I is equal to V over R. So if 50 is V, our voltage source is 600, and then we have 10 ohms here as the load or resistance. Our I will be equal to 600 over 10, and that is 60. So the current is 60. That is why you can see that when you turn the switch on, all right, you can see that it goes to 60 here, and then before it flattens out again. So our I will be 60 amperes. That's how they got to 60 here. So let's take it a step further. Now let's talk about the alternating current. The alternating current is a current with time varying characteristics. So it simply means that from time to time, from one point to the other, the time is not constant. The time is varying. Okay, unlike the DC, where the time is constant. And then what you would have is like a sinusoidal curve. You could have a sinusoidal curve, or you could have a non-sinusoidal curve. In any case, the time is not supposed to be constant. Okay, so when you have a sinusoidal AC, you can see this is a sinusoid. Okay, so you can see moving from the first phase or the first half cycle. This is the first half cycle. Okay, so the first half cycle is 180 degrees. It is half of the 180 degrees that gives us 90 degrees. The fourth half cycle is going to be positive, as you can see from 0 to 10 it's positive. The second half cycle is going down to negative, as you can see, so it's negative. All right, so what makes a full circle is a full sinusoid, which is going from 0. You make the first half circle, and then you make the second half circle, and then you have the full circle from 0 to 360 is your full circle. You have your full circle from 0 to 360, and then you have your T. You can only have your T when you have a full circle. Okay, this is the period. One period is what we refer to as a full circle. Okay, so that's what we do have here. And in the case where we don't have a sinusoid, when we don't have a sinusoid, when the characteristics is not sinusoidal, we have a non-sinusoid. Okay, so you can see we have the current, we have a time here, and then you still have a time varying. Okay, as much as possible, it's not constant. So these are two graphs you should pay attention to and be familiar with. We need to now begin to find out what our sinusoid voltages are, what are the parameters we use to represent the expressions that we have, and what each of those parameters represent. Okay, now a sinusoidal voltage is a voltage with waveform as shown here. I will just explain that to you. It's a voltage with this kind of waveform. Okay, you can see the waveform This is a sinusoid, and then this is a waveform. Okay, you can see the voltage right to the top here. You can see the angle in radians. Okay, so it is usually given as V of t because it is time based. So you can see we have V of t equals to V peak. Though this V you can see with the heart at the top is called the peak, peak value. It is V peak. So you have V peak sine WT, where W is supposed to be your angular frequency multiplied by time plus alpha, where alpha is the phase shift. Angle of voltage at T is equal to 0. They usually call it phase angle, right? That is what we do have here. All right. So this is voltage waveform with respect to time, and then this is our peak voltage. The peak voltage can easily be calculated. It's not something difficult at all. It's usually right at the top here. All right. And then we have our frequency. Depending on the value of the frequency given to you, you can always find your angular frequency. Once you know the frequency, you find the angular frequency, because angular frequency is always 2 pi the frequency given to you, 2 pi f. So when you know f, pi is 22/7, you can easily find your W, which is the angular frequency. The peak is usually this is the peak here. You can see the peak is usually at the vein, where the vein is taking place is where you have the peak, and then you can see we also have another peak of negative, usually called the crest here. So at the minimum here is where you have that. Okay, what else again? You can see we have our phase angle, and then you can see we have amplitude. Okay, this peak voltage is usually referred to as the amplitude. You can see from the horizontal line here right to the very peak here, they call it the amplitude, or the peak value of the voltage. What else again do we need to talk about here? I think pretty much that's all. So this is like a sinusoidal voltage. The waveform you can see here is what you refer to as the sinusoidal voltage. All right. So if we take it a step further, what do we have? Okay, this is just all the things I just explained. We just talked about it again. Okay, so if you draw this on your time graph, you can see we have different timings here. So we have 0 to 5 to 10 to 15 to 20 milliseconds, by the way. So and then you have all the values here. This is just to give you an idea of what is going on. And then if this is like this, we can go forward. Okay, what you will find, like I explained to you, the full period is going to be from from the beginning here until we complete a full circle. So a full circle is going to be this half plus the first positive half plus the second negative, second half, which is negative. So 0 to 20 is going to give us our period. Okay, that's a full period T, which is 20 milliseconds, and that is supposed to be 360 degrees, by the way. So another full circle will be from this point to this point, another full circle will be from this point to this point. So if you convert all of these time to radians or to angle, this is what you're going to have. This is 360 degrees, this is 180 degrees. Okay, this is going to be 90 degrees, half of it 90 degrees. It's going to be 270 degrees. And then you can always, that your frequency is 1 over t, 1 over period. So you can always find your frequency once you know the period. You can always find the frequency once you know the period, and that's going to give us 50 hertz. Sense of it. Okay, so this what I explains a couple of things. So also, like I mentioned the other time, we have a positive half circle. Okay, first half of the circle is from 0 to 10 milliseconds, which is like, in angular frequency it will be in angular frequency, this will represent 180 degrees or pi radians. It will represent 180 degrees of pi radians. Okay, so it is positive, so you can see the current leaving here and going in and then coming back, passing through the load and going and coming back. Okay, you will see that. But then the second half, which is negative, you will see that what has changed here is the polarity of the current. So the current has changed direction. So because it's negative, the current is coming this way and then passing through the load and then to come back to this particular point. Right. So I think this is pretty much a positive half circle, is negative half circle. So you can see the directions of current, and then you can relate with that accordingly. Okay, let's take it a step further. What you will find out is that when we talk about energy storage elements, there are two popular energy storage elements that we're going to talk about. So now that we have a good understanding of the AC circuit, because these energy storage elements, one way or the other, they're found in AC circuits. Okay, so now that we have some understanding of the AC circuits, let us now look at these elements that are important. The two elements that are popular to talk about as energy storage elements for our level would be capacitor and inductor. Don't forget, before now we've been talking about load, which is a resistor. Now we want to talk about capacitor and inductor, which are energy storage elements. Okay, so the symbol for capacitor is usually just two line in parallel, making it look like an equal to sign. So this represents your capacitor, and there's always a voltage across the capacitor, and there you can see current passing through it also. And then we have our inductor. It's like a coil-like, symbol you have here. Coil. You can just coil it in coil-like symbol. This is how to represent an inductor. So you can see we have our L. Okay, capacitor represented with a C, and then inductor with an L. You can see the current passing through it, and then you can see the voltage across it, just right opposite it here. Okay, so we're going to obtain sets of equations, for the circuits of a capacitor and then the circuits for an inductor. We're going to try to look at how we can analyze circuits that have capacitors embedded in them or inductors embedded in them as energy storage elements. So we're going to deal with many questions in regards to that. All right, now what are capacitors? Okay, so elements of an AC circuit, one of them is a capacitor, like we said. What are capacitors? The capacitors can store electrical charge, no doubt about that. So it's a device that can store electrical charge, and it contains two parallel conducting plates separated by an insulating layer. Okay, so as you can see here, we have the insulating layer, we have the positive plate, and then we have the negative plate. Both of them are conducting plate, and then they are separated by this insulating layer that you can see here. Okay, so the insulating layer provides dielectricity. It prevents current flow between positive and negative conductors. Okay, so we have that, and then we have, this is the symbol. We talked about this already. Okay, so that's that. Then if we move from here, we go to now if we have small capacitors, since this is an energy storage element, so we're going to have smaller energy storage elements and bigger energy storage elements. Okay, so depending on the capacity, all right, depending on the capacity of a capacitor is usually referred to as capacitance. Okay, so we have big capacitors, we have small capacitors. When they are big, it means they can store more charge. They can store more charge when they are big. Okay, so they will have bigger capacitance. Just as you can see here, C2 has bigger capacitance than C1 because C2 is bigger than C1. All right. If you want to look at that in the mechanical perspective or in the hydraulic perspective, you will see that we have a bigger storage tank and a smaller storage tank. A bigger storage tank will definitely store more water than a smaller water storage tank. Okay, so if you picture that, you will get a better understanding of what we're talking about here. So capacitors store electric charge. That is a given. Okay, so and we remember that all the time. Capacitors store electric charge. Okay, forward. So as you can see here, these are different types of capacitors. A capacitor plates are packed in a roll form in order to have smaller size. Okay, so you can have smaller sizes, you can have bigger sizes, you can have different types of sizes. As you can see, we have a positive and a negative. Okay, so and they usually have aluminum cover, as you can see in the picture here. So this is a small, this is a small capacitor. This is a smaller capacitor. This is a smaller one, and then this is a big one, the bigger one. Okay, so this is big, bigger, biggest. Okay, so you can see different sizes of capacitors that we have here. That we can use to store electrical. You can use to store electrical charge. All right. So also here you can see, different types. They can be connected in parallel. They're usually connected in parallel, by the way, so to form a bank. All right. So in the bank where we have many of them, we're connected in parallel so that we can have as much energy stored as much as possible. So you can see them here connected together. All right. Also, they usually have what we refer to as a control relay. A control relay acts like a switch. It's like is like an electromagnetic device. Okay, it acts like a switch, so it just stops current from going in, or allows currents to go in. So that is why we have this relay here, basically. Okay, so this is like many capacitors put together, and they're connected in parallel. Okay, so and they store energy, as the case may be. All right, so now this is a single phase capacitor, and it is a three-phase capacitor. Now you should be familiar with some of these things because you must have seen them before. Probably if you have visited an electrical a utility plant before, or if you have visited most of these power stations before, you would have seen this before. Okay, so this is the single phase. You can see we have the neutral, and then we have the positive, and then this is the three phase. You can see we have the red, yellow, and then blue, and then you can see that here. Okay, so the capacitor bank, so they can store charges. All right, so we have medium voltage capacitor banks. When you say shunt capacitor banks, it simply means they are connected in parallel. Shunt means parallel. Okay, we talked about that before in some of the courses some of the topics that we treated. So what you will find out here is that these are capacitor banks. Okay, so if you go to power stations, I've seen this before in power stations. I've seen this before in different places. So these are capacitor banks for medium voltage connections. So same here for the medium voltage. This gives you a bigger picture. Okay, so like I said, probably if you've been to power stations before, you would have seen this too. You can see the capacitors connected. They're all connected in parallel, and all of the stuff here are storing energy. These are big stuff. They're not as small as the small capacitors that we know. There are capacitors for computers. They are going to be small, and then there are capacitors for power transmission. All right, so you can expect how big those are going to be. So we have all of these. So we go on. These are just pictures to give you very good idea and knowledge of what is going on. So we have all of these. So for computers, for motherboards of either computers or other kinds of electrical devices, they also have capacitors. So you can see the capacitors here. You can see them in the motherboard. So they store charges. Okay, this is what they do. They store charges, electrical charges for those devices, and then to make them available when they're needed. All right, so let's take it a step further. What are the basic principles of capacitors? How do they work? Okay, so a capacitor, like we say, it stores electrical charge. Electrical charge is usually given as Q, and then we have voltage that is usually across, passes across the capacitor, and then so there has to be a relationship between the capacitance, the voltage, and then the electrical energy that is stored. There has to be a relationship amongst them. So charge stored in capacitor is pronounced to be the capacitance, represented with C. Charge stored in capacitor is proportional to the voltage applied. So Q is proportional to V. So we can say Q is equal to CV as an expression. Okay, this is the standard expression. Q is equal to CV. So if Q is CV, our Q represents the charge that is stored, and the unit is usually coulombs. And then the voltage is our V, and then the capacitance, which is the capacity of the capacitor, is given as C. So C is measured in farads, and the 1 farad is capacitance with a charge of 1 coulomb at a voltage of 1 volt between the plates. All right, so you can see that. So you can see this circuit here is like a capacitor. We have the capacitor here, and then we have a voltage source here. This is the capacitance, and then we have, if you want to rewrite them symbolically, this is going to be just V. This is going to be the charge across that is stored by this capacitance is Q1 coulomb, and then we have the capacitance 1 farad here, basically. So this is the symbolic representation of what we do have here. Okay, so what is the current relation for a capacitor? Okay, how do we find the current passing through a capacitor? We have said that we have a relation Q equal to CV, right? So, and then if you are considering the time domain, then you can say Q of t is equal to V of t if you are considering the time domain. Okay, so if you differentiate these two, you're going to have the Q to t equal to C dV to t. Okay, and you do know that our I is always equal to dq dt. If you remember that our I of t is equal to dq dt. So if you replace this with I, your I will be equal to C dV dt. Can you see that? So the current in the time domain, the current passing through this capacitance can be given as I of t equal to C dV dt, as you can see here, basically. Okay, so this would mean that once we know our capacitance and then we know our voltage, we can easily find the current here using this expression, as you can see. So we have Q equal to CV, or V equal to Q over C if you're looking for V. If you're looking for I will be equal to C dV dt. Okay, pay attention to this, we're going to use them a lot. So the above equation, if you look at it properly, this particular equation you're looking at here, you can rewrite it and then find your V from here. If you do that, you can rewrite it. If you do that, if you rearrange it, it simply means that I of t over C, I dt over C would be equal to V. If you then integrate, if you integrate it, your V will then be 1 over C integral of I dt. Okay, so that's 1 over C integral of I dt plus V naught, where V naught is the initial voltage across the capacitor. This is very important. The initial voltage across the capacitor, you will always experience cases like that due to initial charge stored in the capacitor. Okay, so and this is not under the integral factor, by the way. This is standing on its own. It is not under the integral factor. Please pay attention to that. Now, if you go forward, or if we go forward, you can see the circuit. You can see the switch here. Okay, so and then you can see all of these as it goes. Okay. If we take it a step further to understand the terminal law for capacitors, as we've been explaining before now in previous slides, you can see this is a circuit for a capacitor. We know that our I equal to C dV dt. We just mentioned that a couple of minutes ago. Our V would be equal to 1 over C integral of I dt plus V of T naught. This represents the initial charge, in the capacitor. Okay. So you can have these, and this can be rewritten as this. All right. So if you take this out, this becomes from minus infinity to t, and then take this V of T naught out, and then you still retain the identity equation, and you move from the limit minus infinity to t instead of T naught to t, basically. The reason we have V of T naught here is because we are moving from T naught to t, so we have V T naught here. But now we move from minus infinity to t, so this T naught disappears, and then we have this the way it is. So these equations are important. Take your time to check this out, because one of the things you have to pay attention to is that the voltage across the capacitor is always continuous. Okay, the voltage it changes. Okay, total charge cannot change instantaneously, so it has to be something continuous. So voltage is continuous in the real sense of it, and the voltage in terms of current can be formulated as we have talked about. And then the only time there is current through the capacitor is when voltage is changing. So if voltage is constant, if voltage is not changing, you will not have current through this capacitor. All right, so the voltage has to be changing continuously, regularly, continuously, for us to have current passing through the capacitor. And dV cannot be equal to 0. That simply means I cannot be equal to 0, because once dV is equal to 0, it simply means current is equal to 0, because 0 is going to be C multiplied by 0, and current will be 0. All right, so these explanations here, and then these concepts of equations and all of these are very important. We've talked about them before, by the way. What you want to look at right now is how to use how to find power, because if we can find voltage and we can find current, then we can also find power. If we can find power, then we can also find energy. Power is just going to be energy divided by time, and then your energy will just be power multiplied by time, and then we can go on and on like that. Okay, so power is usually given as VI. You know that from our Ohm's law and all the calculations we have done in the previous classes. So P is equal to VI, and we do know that our I is C dV dt. Okay, so V multiplied by C dV dt, and then rearranging it, you have just CV dV. Our power can be equal to C dV dt. You keep these in terms of voltage and the capacitance. If you want to write it in terms of another term, since we know our V in the previous slide, you can just bring that in, and then you keep your I here. So it can be V multiplied by capacitance dV dt, or I divided by capacitance with this here that helps. Okay, so these are two different expressions you can use to find the power, depending on the kind of questions you're dealing with, depending on the kind of problems that you want to solve, depending on the kind of project that you're working on. Okay, so this relationship, once we can find power, like I said earlier, we can always find our energy. You do know that power is equal to energy divided by time. So power is equal to dW dt, where W is going to be our energy or work done, okay, with respect to time. So if we have power equal to dW dt, we also know that power is equal to C dV dt. We can say that our dW dt is equal to CV dV dt. Okay, so if we have that dt and dt can cancel out, so you have dW is equal to CV dV. All right, so if you have these here, if you integrate both sides, everything becomes very easy. If you integrate both sides to eliminate this d and have this W to find our energy, W becomes half CV squared. All right, so energy stored in the capacitor can be found using W equal to half CV squared. The power can be found using any of these two equations we have here. The voltage can be obtained using this equation that we have right at the back here. The current can be obtained using this particular equation. Okay, so all of these relationships are very important, and then we're going to be making use of them in solving as many examples as we can. So the first example we're going to try to solve is this. This is the first example we're going to try to solve. Okay, so a 0.2 microfarad. Micro, what does micro mean? Yeah, micro means 10 raised to the power minus 6, so remember that. So a 0.2 microfarad capacitor has a charge of 20 microcoulombs. Okay, so if you have that, find the voltage and the energy. Find the voltage and the energy. This becomes easy because we already know exactly, the expressions to use. Voltage will be equal to Q over C, because we know that our Q is equal to CV. We know that right from time. So voltage will be equal to Q over C. We know Q is 20. Our C is 0.2 microfarad. So 20 over that. 10 to the power minus 6 we cancel 10 to the power minus 6, and then you have 100 volts here as a volt. Okay, I mean, this is just a piece of cake. This is very, very straightforward for you guys. And then to find the energy, our energy can be written as half CV squared, just like we just found out in the previous slides. You can see half CV squared. Our C, we know it already. V, we just calculated it. We know it. You put it here, and then you obtain one millijoules when you put that here, because this is going to be 4 zeros here. This is going to be 10 raised by minus 6. If you check all of those out and you multiply them out, you obtain 1 millijoules as your energy. All right, so this is a very simple example. So here is the second example again that we can quickly look at. Here is a second example that we can check out. Calculate the time waveform of the current flowing in the circuit shown in the right hand side. Okay, so this is the circuit here, the right hand side, by assuming that the capacitor is charged by the exponential voltage shown in the figure. So this is the exponential voltage we have here. This is a non-sinusoidal voltage waveform, by the way. You still remember that? We talked about it a few minutes ago. So V of t is equal to 5 multiplied by 1 minus the exponential of minus t. This is the voltage in the time domain. And then we have it here. So you know what our Vmax is? We all know that our Vmax is maximum voltage, the peak voltage, the amplitude. So maximum voltage that can be reached is 5 from this particular waveform that we are expected to use to solve the problem. So you can see we have maximum voltage is 5 at this particular level. If we know our maximum voltage, then we can find the maximum charge, because Q will just be equal to CV max. Okay, so we have V max. Once we can find our C, we can find the maximum charge. But what are we actually expected to look for? Calculate the waveform of the current flowing in the circuit shown in the right hand side. So we're looking for current and its waveform, assuming that the capacitor is charged by the exponential voltage given here. Okay, so current is going through the capacitor this way, and then we have the capacitor is 0.1 microfarad is what we have on the capacitor. Okay, so let's take it a step further and see exactly how to deal with this. Okay, now our I of t is equal to C dV to t. You know that, right? We've talked about this before. V of t has been given to us, so we can easily find our dV dt. What is going to be our dV dt here? You can easily see that V of t is equal to 5 minus 5 exponential minus t. You can say that if you want. Okay, so if you want to differentiate that, your dV of t dt, differentiate with respect to time, will be equal to, this is going to be 0, right? If you differentiate the constant, isn't it? If you differentiate this minus the coefficient of t here is 1, so minus 1 goes to the back, this becomes 5, isn't it? and then you have the exponential of minus t. So dv dt will be 5 exponential minus t. You get, okay? So I want to believe you still remember how to do all this differentiation. So from here, our I of t is equal to c dv dt. So I of t will just be equal to c multiplied by 5et, which is exactly what we have here. Our c is 0.1, by the way. So if you flip back this particular slide, you will notice that our c is 0.1 farad. So if you come back here, you find out that our I of t then becomes 0.1 multiplied by 5 exponential t. Can you all see that? So if you multiply that, you have 0.5 exponential minus t amperes. This is going to be your I of t. All right. So if you have your I of t, this is our v of t, and this is the waveform you have here for the v of t. So how do you get the waveform for I of t? This becomes very easy. Okay, for every value of t that we have, we find your I of t starting from 0. If t is equal to 0, you have exponential t, exponential 0 here. What is exponential 0? That should be 1. 1 multiplied by 0.5. That gives you maximum current of 0.5 at the top here. Okay, so when t is 0, current is going to be 0.5. What happens when t is equal to 1? When t is equal to 1, we have exponential of minus 1, right? Exponential is usually given as 2.718. Okay, so 2.718 raised to power minus 1 multiplied by 0.5 will give us about 0.1 something. Okay, so if you multiply that out, you're going to obtain, at t is equal to 1, you're going to get a value here, and then that value is going to be here, almost 0.1 plus 0.1 something is going to be how, and then you have it 0.13 or so. If t is equal to 2, you put that here, you obtain your I, you obtain something, you put it here. If t is equal to 3, you obtain something, and then you join all of those points together to form this particular curve, and then you have a current wave form. Are we all good? Any questions? We all following? What are we looking for now? Now determine the time waveform on the charge stored on the capacitor on the same circuit. Okay, so we have determined the time waveform for the current. We have the time waveform for the voltage already as given right at the back here. This was given the question. Now we found the time waveform for the current, as you can see here. Okay, now we want to find the time waveform for the charge. All right, how do we find charge? Our charge is usually CV. We know that already, and we know our V already. So, and we also know the capacitance, which is 0.1. Okay, so 0.5 multiplied by this gives us our charge. So our charge will be 0.51 minus exponential t. So that simply means for all times from 0, 1, 2, you just keep varying the time. 0, 1, 2, 3, 4, 5. You vary the time until you get different values of charge for time. Once you do that, you're going to obtain a curve. You're going to obtain points in these, and then when you jump the points, you're going to obtain this particular curve here for all the various times that we have. So you can see we have the time waveform of the charge also here. So this is pretty much easy to handle and deal with. If you have any questions, don't hesitate to ask.